So today we're joined by Dr. Jean-Francois Ayme, who's coming across from the Department of Chemistry, where he works in the Cooper group, I guess. So yeah, today we're hearing about how you put a brain, a literal brain, in the robot chemist.
Almost, yeah. All right, so thanks a lot, Alex and Naomi, for inviting me and giving me the opportunity to present the work we are currently doing just next door in the chemistry building on mobile robotic and AI for chemistry. So, seems like it's very slow. So, robotic and automation has permeated most industry nowadays. And here you can see an example from the supermarket brand Ocado that is using this swarm of robots called the Hive to prepare the basket of their customers. And of course, chemistry is not escaping the trend. So in the past 30 years, the cost of automated solution for chemistry has gradually declined, and also the market share of robotics for chemistry keeps on increasing, and we foresee that this trend will continue in the foreseeable future. And so a couple of group and industrial groups around the world have already proposed solution for automating chemistry, and you can see from this slide that they all look very, very different. So there is no consensus for the moment. And I just want to show you our flavor of automated chemistry here in Liverpool. So the main concept that we are using as a main line for designing our automation lab is that the most expensive piece of equipment that you will have in a chemistry lab usually are the analytical equipment that we are using to analyze the reaction to check what was the outcome. And usually this piece of equipment are highly specialized, and they are all designed to be used by a human. So of course, anything that can be used by human can be automated. But if you have like 5 different machines with 5 different setups, then the cost of automating your entire lab is increasing exponentially, and it's getting very difficult. So we arrived to the conclusion that it might be easier to automate the chemist rather than to automate the equipment. And that's a strategy we applied successfully in 2020. So here the concept was really to use this mobile robot as a drop-in solution in an existing lab. So that you don't have to customize any of the piece of equipment that is around the lab. You don't have to customize any of the expensive analytical equipment. You can just drop your mobile robot, and it can roam around and operate the different stations. The other advantage compared to human researcher is if you hook the robot with, for example, Bayesian optimizers, and you can solve problems that are very high dimensional. And of course, contrary to a human, a robot doesn't get tired very fast. And so you can really do a lot of work. And I'm going to try to convince you that this robot did a PhD in a week. So of course, something has happened in 2020, if you remember, that's COVID lockdown. So the concept of having a mobile robot operating lab autonomously with minimal human intervention was quite effective for the press, and this work got quite a lot of coverage in the British media. So what can our robot do? So our robot can do most tasks that most basic tasks that a human chemist can do. Can dispense solid, can dispense liquid, can also place the vial with the reaction in the right reactor. In this case, it's a photoreactor here, because the reaction we were studying was photocatalyzed. So robot can also operate the analytical equipment that is required to assess if the reaction was successful or not. In this case, it's a gas chromatography GCMS, but we'll see later we can use many different pieces of equipment here. So in this slide, I'm going to show you the equivalent of 48 hours of autonomous operation by the robot, summarized in 60 seconds. So you can see the robot going from the solid dispensing station to the liquid dispensing station, then the capping unit. Capping unit is the only highly customized piece of equipment in the workflow. And it was required here to just build something custom due to the nature of packing and in atmosphere is not easy to achieve. Then the robot drive to the photolysis station where the reaction are irradiated for 1 hour, and then the GCMS is doing the measurement to assess how much hydrogen was produced in this case. So you can see that the number of samples tested is increasing by 16 each time. It's because like the robot and the workflow runs in by batches of 16. And compared to a human experimenter that would do the same workflow, so preparing the sample, letting it react and doing the measurement, usually human chemists can do between 2 and 4 samples per day. So here, after 48 hours, we have done 192 samples. So it's almost a 100-fold increase in efficiency compared to a human chemist. And the other thing that is very important here is the robot is not just performing the experiment. There is a Bayesian optimizer running in the background. So we're also optimizing the reaction at the same time. So I'm not going to enter in detail at all in the chemistry, but the goal is just to maximize hydrogen production from water suspension of like many different components. So we have several different hypotheses that we hoped would impact how much hydrogen is produced. So the first hypothesis is how much catalyst you have. So that's the compound responsible for producing the hydrogen. The presence or not of a scavenger, here cysteine, the presence or not of dyes, that will dye synthesizers that will help to help the catalyst to be more active in theory. Also controlling things like pH, how acidic or basic the medium is, like the presence of salt or the presence of surfactant, because of course you have organic molecules in water, so everything is not soluble. So overall, this represents a search space of 98 million possibilities.
So to reject the phosphorus?
Yes.
Okay, I'm worried about on. Oh, okay, it's just one person on one campaign, but everyone else one.
Okay.
You
Sorry. Yeah. Hopefully the recording will be enough. So in this slide, you're going to see in the bottom corner the robot performing the experiment over 8 days, and here you have a graph of the catalytic activity of the formulation we are using versus the number of samples. So the black line here, you see the black dot is just the baseline that we took before the optimization, just to be sure that the setup was stable. And after 8 days of autonomous optimization, we end up with a formulation that is six times more active than what it was initially. And if you look at the radar plot on this side, and you can see that like the surfactant and the dyes were selected, they're not kept at all. They were not found to be beneficial to the reaction. Salt were found to be neither good or bad, very neutral. So the Bayesian optimizer prioritized components in the reaction that were more impactful, such as the two base and the scavenger. So one point that I want to highlight here is how Bayesian optimization is thinking differently to human chemists and how they approach very differently the problem. If you look at how the Bayesian optimizer explores the part of the space containing the base sodium hydroxide, you can see that at the beginning of the experiment, for around like 100 experiments, it uses sodium hydroxide. And then because it probably didn't get very good result with sodium hydroxide, drops it entirely for 50 experiments before re-exploring this space later on. And if you think about it as a human, if you have bad result with a parameter with one reagent for 100 experiments, you don't use it at all for 50 experiments, you're probably never going to come back to it. But the advantage of Bayesian optimizer in this case, it keeps always full memory of what has happened earlier, and it can reprioritize the exploration of a given portion of the space when it gains more information on the problem in general. So while this project was quite successful, overall, if we are looking at it very objectively, it's a very simple formulation problem. And the platform is not capable of doing very complex chemistry. Also, there is no real understanding by the bio of any chemistry per se. So if you wanted to scale this to a more complex problem, it would not work. So the next two things that we try to, in our follow-up work, we try to address these two problems. So the first thing we tried to fix is increase the synthetic capability of our platform. So have a more general platform for synthetic chemistry. And also we wanted this platform to be still autonomous, but focus now more on the question of discovery rather than optimization. And you will see later that is a massive difference in terms of like how the decision making is operating. The other thing that we wanted to keep is this concept of using only non-customized equipment, especially for the expensive piece of equipment, such as in our case, the nuclear magnetic resonance instrument and the mass spectrometer, which are very expensive. So the concept here is we have our automated synthesis platform that is going to prepare the sample. Then we have our mobile robot that is going to carry the sample from the synthesis platform to the analytical instrument. And these two instruments are going to remain completely unchanged to what they were when we bought them. So that when the workflow is not using them, when the workflow is not recording data on them, they remain available for human to use or for other workflow to be used. So you maximize the usage of resources, which is very important, especially in academia where resources are limited. So one point that I want to highlight here is the difference between an automated lab and an autonomous lab. In the case of an automated lab, human is taking all the decision, and the robot is just here to perform the experiment. Whereas in the case of an autonomous lab, then part of the decision process, and maybe in the future, the entirety of the decision process is also offloaded to the robot, not only performing the experiment. So what is decision-making process looking like, especially in the case of discovery? So the case of discovery is slightly more complex than optimization, because in the case of optimization, you are just going to track one single well-defined metric, like for example, the yield, how much product your reaction made, and it's very easy to track. Whereas in the case of discovery, usually discovering something is inferred from a signature, like for example, what NMR spectra look like the pattern. What is the mass of the compound you form in a given range? It's not an exact number. It needs to be this mass, or it needs to be this precise pattern. No, it can be a range of patterns that is valid. It can be a range of mass that is valid. And so in this case, we argue that having a decision-making process based on heuristic rules designed by a chemist is much more efficient than relying on any AI model. The other problem being, of course, if you work in discovery, usually you don't have, especially in chemistry, massive data set available to train any model. And acquiring the data required to train one of these models would be extremely, extremely expensive. So we stayed with heuristic rules. So the concept is we do the synthesis, then the sample are ferried by the mobile robot to the mass spec and the NMR. Then the analysis is recorded, and then we use a basic set of heuristic rules on each analysis to decide if the reaction was successful or not. But you can see there is a second step where we combine the result of both of these methods to decide if a reaction is successful or not. And that's addressed another pitfall at the moment of many automated setup in chemistry, is because most setup out there use analytical instrument in line with the synthesis platform. So that meaning that the analytical instrument is completely monopolized by the synthesis platform. You can only dedicate so much instrument to this workflow. So usually people will just rely on NMR alone or mass spec alone. But like in many science, in the case of chemistry, each of these analytical technique is not giving you the full picture of what happened in your reaction. You can only have the full picture if you combine many of these techniques together. And kind of gold standard in chemistry is really combining NMR and MS, is giving you kind of like a very robust assessment of what happened in your reaction. So that's what we are doing here. We are combining the result of both analytical method to decide which reaction was successful or not. Then we feed back this information to our reaction planner, and it decides automatically what the next step is going to be. So what this setup looks like. So here is our chemistry synthesis platform. Here's our benchtop NMR, and here in the corner is our MS platform. And you will see in a second the first mobile robot approaching the chemistry. So now the chemistry is opening automatically. This piston is the only simulation we have done in the workflow. Then the robot calibrates its position, picks the rack of MS vial containing an electrode of our reaction, and drives all the way through the mass spec. Once again, it calibrates its position to be sure it's not drifting too much while moving, and deliver the samples. Then the acquisition of the mass spec starting automatically. Now you will see in a second another robot coming from the other side of the lab, and this time this one is going to pick the rack of NMR tube for the NMR machine. So of course you are going to tell me here, oh yeah, but you could have done this with only one robot. And yes, it is the case. We can do it with one robot. So the reason why we use two robots in this case is just to show the scalability of this technology, because ideally in the lab of the future we will have more than one chemist in this platform. You might have like 20 of them, and maybe you want more analytical instrument. Maybe you want a UV spectrometer and IR. And so in the future, we will potentially need more than one mobile robot, and we really wanted to show that we can use more than one of them. So I'm not going to enter too much in detail in the chemistry that we have studied here, but you can imagine this system a bit as artificial enzyme mimic. So the concept is we have a molecule that has the shape of a pyramid with a cavity in the middle that is empty. And of course, like an enzyme can bind to a substrate, this empty cavity can bind to other smaller molecules that are around. And which molecule is going to be bound by this cage is depending on the shape of the cage. And the reason why we pick this chemistry, it goes back to this concept of discovery. It's very difficult to determine a priori what the outcome of one of these reactions initially is going to be, what type of architecture you're going to obtain from this building block. So it's really, you cannot have like a rigid rule saying like look exactly for this type of architecture. It's very hard to predict. So the first step of our workflow is called the combinatorial screening. So in each reaction vial, we are going to mix one carbonyl compound. So it can be compound 1, 2, or 3, one polyamine, so either 4, 5, or 6, and one metal, either zinc or copper. So in total, it's 18 possible combinations. We are going to try all of them, and then we use our set of heuristic rules to decide, or at least for the platform to decide which reaction was successful or not successful. So reactions that were found to be successful are then pushed to a second stage of replication, where they're going to be each reproduced 6 times, just to be sure that this initial find is not a fluke and that you can make it repetitively. Then we use this replicated sample to test a function of this architecture, which is, can it bind to another molecule? And overall, the workflow is operating autonomously for 3 days with minimal human intervention after the human have initially set what the problem was and set the heuristic rules. After that, the only human intervention are restocking once a day for 20-30 minutes, where you just need to put fresh vial, fresh NMR tube, a bit more reagent, fresh solvent. So going back to this decision-making process. So as I said, like in the context of discovery, because you don't have like a clear number, standardized number that you're tracking, you need to have loose boundaries to decide what makes a successful reaction or not. If your rules are too strict, then you are going to find no positive. If your rules are too loose, then you are going to have very false positive, many false positive. So we ended up just using 3 fairly simple rules to assess if a reaction was successful or not, and they worked very well. So the first one was for the mass spec is we pre-computed many possible complex. like around 40, 50 per reaction. And we were just looking if we were obtaining one of the hits for one of these plausible products. For the NMR, the selection criteria were more based around did a reaction happen and how clean this reaction was. So the first criteria is like, are the signals in NMR moving? It's just a proxy to see if any reaction happened. If the signals are not changing at all compared to the reagent, then it means that there is no reaction. Here, they move means that there is a reaction. Then the second criteria for NMR is how many signals we have in the reaction mixture compared to the reagent. If all of a sudden we double the number of peaks, that means that we are not forming one product, but we are forming many, many different products. The reaction is not clean. We don't want to keep it. So we can see a couple of examples here very quickly. So in this case, we can see the NMR is no signal shifted, but so means that there is no reaction, and the mass spec confirm it. There is no product observed in the range we expect them to be. In the second case, we can see now there is a reaction because the signal have shifted. The number of signals is okay. So I mean it's a clean product, but once again, mass spec is saying no. So for caution, we just discard this reaction also. In this case, we do have a hit in the mass. We clearly have shift in the signal, so it means that we found one of this interesting architecture. But you can see now we have many, many signals here compared to what we had before. That means that even if we form one of these interesting architecture, it's part of a mixture of many other things. So once again, we discard it. And finally, we have the case where all three conditions are reunited, and this was indeed one of the confirmed architecture later. For replication, then the rules for success are very easy. Is that can we replicate exactly what you obtained before during the screening in the mass spec and in the NMR? For the host gas chemistry, so for binding this external molecule inside the cavity, once again, we have to anticipate for the unknown, meaning that our rule need to be flexible because we don't know how much the binding of the gas is going to affect the NMR signal of the cage. And so we just ended up using a very simple rule of have the signal shifted compared to the initial reaction mixture when we add the gas. And mass spec in this case is not very informative. So of course we have tackled many different flavor of chemistry. Like this workflow now is more something you would find in a big pharma group trying to find new APIs, where you start with the initial promising building block and you quickly try to generate a library of many different compounds by subjecting them to a series of different reactions. So here, once again, we have combinatorial screening at the beginning. Then the reaction that were found to be successful as this time scaled up instead of just replicated. So we just make a lot more of it. And this allows us to confirm that the reaction works again, and also to have more material for a second reaction to create more diversity. So once again, the workflow is operating fully autonomously for 4 days with minimal human intervention. And you can see that after these 4 days, we were able to make 12 new compounds out of the expected 16, with once again, like almost no human intervention besides restocking. All right, let's switch a bit from automation of chemistry to like maybe more AI topic. Is we have seen that we have increased the synthetic capabilities of the robot, and now the next step is can we increase the reasoning capabilities of our workflow? And the first flavor of this that we decided to explore is high bio. So can we inject human hypothesis into a Bayesian optimization to increase its efficiency? So as a toy problem, we picked basically the same chemistry than I presented earlier in the talk, and we just extrapolated the missing data point based on the 700 experimental points we had. And once again, the goal is to maximize hydrogen production. And of course, if you walk around the chemistry building and you ask 10 different chemists their point of view on what factor should be important to increase the hydrogen production, you will have probably as many answers as you have chemists. And some of these hypotheses agree, some of these hypotheses strongly disagree. And what's nice is if you feed all these hypotheses at the beginning to the bio, then you do obtain a slightly more efficient process where you have faster conversions. So even if the hypotheses are not perfect and you have a mixture of like good and bad hypotheses, the Bayesian optimization process will be able to select the ones that are right and discard the ones that are wrong, and generate a process that is more efficient at the end. So here you have an example of like in the previous case, the hypothesis that we are feeding to the model was in between, neither very good nor very bad. And so what happened now if you have a very bad hypothesis? So the beauty is like this high bio will discard very quickly the wrong hypothesis if they don't lead to any improvement. And then an hypothesis is only going to be kept as long as it leads to an improvement. So for example, this one is kept all the way along the optimization because it kept on giving improvement. So of course it's 2025, so you need to put LLM in the talk, and if you can have human producing hypotheses, you can probably have an LLM producing hypothesis also. And how good are going to be these hypotheses? So it turns out that if you use an LLM to generate the hypothesis during the Bayesian optimization, it's even better than if you just ask a human. But to be fair, this comparison is not very fair because like the two Bayesian optimization don't work exactly the same. In the case of the human hypothesis, we have a set of hypotheses that is generated at the beginning of the optimization, and this set of hypotheses is kept all the way along the optimization. Whereas the beauty of the LLM is like they're available any time of the day. So if it's 2 a.m. and you have your next batch of sample that is finished, then you can ask an LLM, what do you think? And it's going to reply to you even if it's 2 a.m., which is not the case of a human. So you can have like a much more dynamic set of hypotheses that is updated after each sampling. And the other big difference between these two Bayesian optimization process is also like the initial sampling. So in the case of the human-led bio, we were just relying on random sampling, whereas in the case of the LLM-led bio, we ask the LLM, what do you suggest as initial sample? And we can see that it always places us in a much better position than just random sampling. So how does it work? So we create what is called an experiment card that we feed to the LLM. So the experiment card contains context about the experiment to optimize, also some constraint on the input space, a description of the different parameters and their boundaries, so just to know how much of each reagent it can add, and also what is the target to maximize. Then we feed this experiment card to the LLM with one review article on the topic we are studying. In this case, I have photocatalyzed hydrogen production. Then the LLM is going to come up with an initial set of hypotheses on what parameters are going to be important for the reaction or not. And then for the optimization process, so it's a hybrid optimization framework based on Gaussian process uncertainty. So meaning when the uncertainty of the Gaussian process is very high, so meaning when the Bayesian optimizer has a very bad understanding of the space, it will default to the LLM. And in this case, the LLM is found to produce more intelligent suggestion of reaction to sample next. When now the uncertainty is moderate, then we'll have the bio generating a set of possible experiment to sample next, and the LLM is going to pick from this set of experiment which one to actually test experimentally. And once the uncertainty is very low, now like the Bayesian optimizer has a very good understanding of the search space, then only the optimizer is deciding what to sample next. What is also nice with having an LLM in the loop is after each sampling, when you get the result of the sample, it's going to produce a report of what has happened so far in the optimization, and it's also going to dynamically update its hypothesis. And you can see that what is nice, it's fairly human readable, and you can really get a bit more insight on the optimization process. For example, in this case, you can see that the optimizer thought at the beginning that the presence of base and dyes will be extremely detrimental, but then after 20 experiments, it was reinforced into its belief that base were bad. But now, after 240 experiments, his belief changed. He said, "Oh, maybe bases are not that bad at the end of the day," and in fact, even switched to classify them as good with a medium confidence index. So, are LLMs the answer to all our problems? No. I mean, if you try to optimize the reaction just with the LLM alone, you can see that despite a very good start, you plateau very fast. It's because LLM don't have any mathematical rigor behind the optimization like a bio would have. Doesn't have like any understanding of certainty. So in this case, in the case of Bora, why it works so well is because it's really bio remain at the core of the reasoning engine, and the LLM is just here to improve the efficiency of the process by suggesting more intelligent things to try, and by having this dynamic hypothesis updates. And this concept of LLM-led bio has been tested on many different other problems than just hydrogen production. And you can see that in each case, the green curve is kind of at the top or among the best performers. So all in all, since our initial work on mobile robots for chemistry in 2020, this concept has picked up some speed around the world. And we are very excited to see where this entire field is going to go in the next few years. So I just wanted to thank Andy for being an amazing PI and really like creating a great atmosphere to work in this group, and of course like the entire Cooper group for being amazing co-workers, and all of you for listening.
Thank you. So I'll take questions from the room first. If anyone online has got any questions, either drop them in the chat or just raise your hand up and I'll invite you to unmute yourself. So any questions in the room? Yeah,
when you're doing this, just out of curiosity, if you were to get a human to read the review article you produced,
yeah,
would that have been closer to the LLM rather than the I mean, I don't know how much of a cartoon it was, but you had one person hates bases, one person loves bases, and you the diametrically opposed things. It seems excessive.
I mean, the hypotheses that were used in the human-led hypothesis bio were generated by chemists with a decent knowledge in this field of chemistry to start with. So no, I don't think it would improve a thing to give them a review. It's just like the problem with chemistry is like sometimes so complex that two people, even from the same field, will have very different opinion on a given reaction.
I just wondered if having things sort of so out of line was setting it up to fail because you've sort of given it conflicting information.
Yeah, but as maybe I didn't do a good job of explaining, but like bad hypotheses are not going to impair the optimization too much because they are dropped very, very fast. Okay. So if they don't show, if a given hypothesis is not giving improvement after one or two sampling, then it's going to be discarded. So like even very bad hypotheses are not too detrimental. Yeah.
Thanks. Okay. Any questions? If not, So where do you go next with this? It's already like a really impressive piece of technology. What's the next step to improve this?
So the next step is really to merge this LLM build with the latest, more capable synthetic platform, so we can tackle more challenging chemistry and benefit from better optimization. Yes.
Okay. Do you think you're at a point where you're using LLMs to sort of pose research questions? So it's not just a sort of
design everything from the beginning, design the experiment.
Yeah, don't just do the PhD, also do one application, do the supervision, all that kind of stuff.
Yeah, I mean, like where we found LLM is very powerful is doing very basic reasoning tasks that just take too much time as a human to do. Is like as soon as you ask them to reason on too high level, then they're just going to produce suggestions that are less good than human.
Yeah.
But they're very good at producing basic level of reasoning and doing this very repetitively. So, like in the case of the Bayesian optimization, like who has time to, if you have if the sampling of your space is every 2 hours, who has time every 2 hours to look at the batch of 16 samples and draw the hypothesis? Oh yes, this has changed. So my new belief is this.
Yeah.
It's like too time consuming, and also like it's too much for a human brain to handle. It's like too much information in a short amount of time. Whereas for the LLM, it's okay. It's at the end of the day saying like, oh yeah, for these 3 points, like each time I added some base, the reaction was less performant. It doesn't take like a massive level of reasoning to do this. And the LLM can do it at scale at any time of the day. And that's one of the main points of LLM and why they are so good, we think.
Have you tried different LLMs? Like I know some of
No, at the moment we have not tried different LLMs, but like other group have done so. And in this case, it's 4O mini, I think we use, which is quite outdated by now. So potentially with like more modern LLM, they would be capable of tackling more difficult reasoning tasks.
Could this have implications for, say, like scientific reproducibility? Because, like in theory, you think if I've got the same precursors, I've got the same floor plan, I've got the same equipment, I've got the same robots, you should be able to make basically the exact same experiments campaign that a different research group did.
Yeah, I mean, that's the entire point of like automation in chemistry, is to really have like a highly standardized data that is in theory highly reproducible. Yes, that's the reason why there is a push for automation in chemistry, because that's still it's still one of the problem in chemistry today. Is like because we rely on human experimenter, like details that end up mattering a lot for the outcome of the reaction are sometimes lost. So if you have 2 human chemists and the only thing that is written in the prep is add reagent B dropwise, like dropwise for Bob might be 2 minutes, and for John it might be 20 minutes, and at the end it's going to completely change the outcome of the reaction. Yes. So yeah, standardization via automation is a very important step in chemistry.
Okay. Okay, so 10 years from now, what does a PhD in chemistry look like? What is a PhD student in chemistry actually learning to do? Are they learning to do these experiments themselves? Or are they...
Yeah, I think you still need to have like an overall understanding of chemistry, and like you designing the core problem the autonomous platform will study. It is going to remain the role of the human chemist, but then all this LLM and automated workflow is just going to free a lot of time for the chemist to invest more in thinking rather than spending time in front of the fume doing like a boring addition over hours.
Yeah.
Yeah. So just like freeing up time, just an efficiency tool, basically.
Any questions?
I was just wondering, is there any safety considerations that don't take I mean, I don't know that much about chemistry, but you're applying the LLM to say what you're going to mix.
Yeah.
That sort of form.
Like in this case, like because we control when we design the space, we kind of control for this. We will make sure that we are not using highly toxic or highly explosive or highly dangerous chemicals. But yeah, that's a true concern. If you have like a really to go back to the question, like, are we going to have like LLM one day designing everything from scratch? Then yes, this would be a problem, because then you need to be very careful what you select. But we have like work ongoing now where LLM can also be useful for managing safety in the lab. So for example, they're fairly good at doing basic image recognition. So you can have like camera across the lab and then taking like a snapshot every 5 minutes of the lab and feeding this to an LLM and asking, is everything fine in the lab? And then the LLM will be capable of saying, oh no, there is a fire, and then trigger the response, the appropriate response. But yes, safety for this kind of autonomous workflow is something to be considered. Yes.
So just on the safety point, is the computing being done on like local servers or like on the cloud or?
No, it's local server at the moment. Yeah.
Okay. So I guess, do you have to take in the extra like cybersecurity concerns? Because you can imagine.
I mean, like the computers, like the computers that handle all of this is not on internet.
Okay.
During the workflow running. So
yeah. What was the process like getting this past the IT services? You're gonna have this kind of closed-up environment.
It's a public recorded lecture. I'm not going to discuss the matter now.
Okay, we'll edit this bit out. David?
How much do you think in future this is going to be a standard feature of labs, so that you don't need the robot because the machines will just have it built into them? They just have a conveyor belt or something that just moves between stations. It does feel like the robot arm is very much a retrofit of sort of this is the robot chemist, but obviously, much like production lines for cars, or whatever, you would want your devices to be more sort of production line friendly.
I think it's still a long way from now, because one of the big problems of chemistry is the diversity of reaction and the diversity of possible outcome. Like for example, like if you look at peptide synthesis, it's a very standardized reaction. If you do the same reaction, you have the same building block that's used ad nauseum, and so therefore this was automated like almost like 20 years ago now. Whereas there is no good solution for automated chemistry in general still nowadays, because sometimes chemistry just minute change in your structure might make your compound completely insoluble, and so now you have to handle solid, and your platform is not ready for this. And you have too much diversity in terms of like the condition you need to use for a reaction to make chemistry easy to automate. If you think about an assembly line for car, like the robots are repeating always the same task, it's very easy. But you cannot really have this in chemistry. If you say, oh yeah, separate these two organic and aqueous phase. Some solvent, like the aqueous phase is the bottom, organic is the top. Some solvent is the opposite. Maybe your reaction is producing a big emulsion and you don't have clear separation. Maybe you have some solid precipitating, and so on and so on and so on. Like this really diversity of possible outcome really makes automating chemistry very, very challenging. And that's the reason why there is no good solution still today.
So in the intermediate steps, when it's lifting the vials out of one step and moving it to the other, does it actually have some sort of test to say this should all be a liquid, this should be two liquids, one on top of each other, this should be a solid?
No, we don't have that at the moment. But ideally, yeah, we would implement this. Yes, some basic computer vision just to check that if everything is uniformly soluble. Once again, here in this case, because it's a proof of principle, we selected chemistry where we knew that the probability of this happening was very, very low. But if you have like a video platform that's supposed to tackle any chemical problem on demand, then yeah, you will face this problem.
I just wondered if there was any risks. Obviously, relatively expensive machinery. If your robot randomly dumps things that it shouldn't be dumping into that because it doesn't know any better.
Yeah, no, exactly. Yeah, that would be a big problem. So at the moment we circumnavigate the problem by just designing intelligently the space we're exploring. But yeah, if you want a very general purpose platform that you can really like plug and play with your chemistry, then this would be a concern. I don't think it would be easy to find a solution to this. Yes.
Any more questions? I think last one from me then. Is this a protected technology in any kind of way? Because you could imagine kind of groups with a lot of money and some nefarious purposes could look into making synthetic recreational drugs that are very similar to opiates or whatever. Are going to making these things.
No, it's not. It's not protected. It's the same for like other platforms developed around the world, like the computer in Glasgow.
Yeah.
I think if you're a very talented engineer,
yeah,
and a chemist in
yeah,
you can make it work. But I think like also the technology is at a point where, as a proof of principle, we can make it work. But still, human chemists at the moment are still more efficient than using this technology. Sure. So I think like for nefarious usage, you better hire a chemist. Yeah.
So you still have a second career on if you want to.
Exactly. Yeah.
Yeah.
You said I think that you do 6 replications just to guarantee your results. Is that
exactly?
Or is that something that you do because
no, it's exactly. It's not typical in chemistry. Like sometimes people will do replicate, but for some synthesis, people will just do the reaction like once or twice. So it's really because we have the robot, we can replicate for lower cost in terms of like manual labor, in terms of labor, that we could do so many replication. So yes, that's another big point of automation. It facilitates replication. So more standardization, more replication at lower cost, and so on and so on.
That's possible. Because when you publish the results from this, as you were saying, sort of, the traditional drop in the solution, drop in the time, whatever, can you actually say at a very, very precise level of using this machine or these settings on this machine, do this so that it is 100% replicatable to sort of the machine like the out of calibration, something at least anyone else should be able to replicate this exact.
Yes. So for example, using the chemspeed, you have to write the program in the chemspeed where you specify all of this. You specify the addition rate, the volume you're going to add, and so on and so on. So all of this is reported. And if you look now a bit outside of what we do in Liverpool and for example what Electronin is doing in Glasgow, he has written like a Python wrapper called KDL that is exactly doing this, where you have to enter in detail every single step that you are doing, so you have all the detail available. So instead of publishing like a vague prep like chemists are doing at the moment, where like the compound was added dropwise, it's really specified the compound was added 2 mils per minute over 10 minutes. Yes. And you can get this information easily even on our platform because like the way the synthesizer is programmed, you need to standardize this.
So that would be published publicly as part of results when the results come out of this system.
Yes and no. Yes and no. In the case of KDL in Glasgow, it's very easy to dump all your Python code on Git or something like this. In the case of the chemspeed, because it's a proprietary API, it's very difficult to extract the information from the API in a format that is easily human readable. So yes, you can do it, but then it's going to be 50 pages of screenshots. Unfortunately, due to the nature of the API. So ideally, that would make the API more open and easy to interface with Python, and then we could generate all this data and put them in DSI publicly available. Yes, ideally we will do this.
Cool. All right. Well, thank you, Jean-Francois, one last time.
Thanks a lot.